Okay, we're going to get started. My name is Christopher Merrill, and as the director of the International Writing Program, it's my great pleasure to welcome you to this lecture by Margaret Wertheim. Before we start, please silence your cell phones. And for those who are planning to attend the talk by Charles Ray at 7 o'clock, I want to assure you that there will be plenty of time for you to get there. Margaret's going to talk for about 45 minutes, and then we'll have a Q&A. So sometime after she talks and in the Q&A, if you need to beat a retreat, you can do that. This lecture is part of Creative Matters, a year-long series of events sponsored by the Office of the Vice President for Research. And I wish to single out for special thanks Dan Reed, whose support for the arts and humanities is crucial to the life of our community. Creative Matters, which brings together artists, writers, and thinkers to discuss the creative process, grew out of the Arts Advancement Committee, convened by Provost Barry Butler and Dean of the College of Liberal Arts and Sciences, Chadin Jalali. Co-chaired by Alan McVeigh and Chuck Swanson, our charge was to synthesize energies, forge connections across disciplines, and spark new ideas in conjunction with the rebuilding of our arts campus. The flood of 2008, which did so much damage to our community, has also inspired a building boom, which we hope to match in various artistic and intellectual ways. Creative Matters is the brainchild of David Geer, George de la Peña, Ann Ricketts, and Leslie Weatherhead, whose tireless efforts make occasions like this possible. And let me draw your attention to one more event in this series, when on April 12th, we will host a talk by Sarah Lewis, author of The Rise, Creativity, The Gift of Failure, and the Search for Mastery. More details to follow. This is in keeping with Beckett's idea, fail again, fail better, at the heart of the creative enterprise. But tonight we have the good fortune to welcome Margaret Wertheim to campus. She is an acclaimed writer and curator, originally from Australia, whose work focuses on relations between science and the wider cultural landscape. She is the author of 6 books, most recently Physics on the Fringe, Smoke Rings, Circlions, and Alternative Theories of Everything, whose epigraph begins with the delightful sentence by Michel Foucault, "I dream of a new age of curiosity." Ms. Wertheim is a writer whose curiosity seems to know no bounds, and in her work she reveals herself to be a gifted and audacious explorer, discovering at every turn new ways to think about our place in the scheme of things. We find her at the intersection of science and art, looking in both directions, and what she sees is at once riveting and revelatory about the wonders of this world. Ms. Wertheim is also the founder and director of the Institute for Figuring in Los Angeles, which describes itself as an organization dedicated to the poetic and aesthetic dimensions of science, mathematics, and engineering. In this capacity, she has designed exhibitions for galleries and museums in a dozen countries, all of them rooted in her belief that abstract ideas can be embodied in physical practices. She invites audiences to play with ideas, a concept that may remind this audience of the pleasure we took in Theo Janssen's talk about his Strandebeests. And I suspect that many here are among the 1 million or more viewers of her TED Talk about the Crochet Coral Reef, a participatory science and art museum which she and her twin sister Christine have created and showed at the Andy Warhol Museum in Pittsburgh and the Science Gallery in Dublin, among other places. In this conjunction of handicraft and geometry, we are presented not only with mathematical truths, but a warning about the role of global warming in the degradation of the oceans. Art and science, joy and alarm, they come together in Ms. Wertheim's dizzying and dazzling work. Please join me in welcoming her to the University of Iowa.
Hello, is that live? Yes. Well, thank you. It's a real delight and honor to be here, and I'm particularly thrilled to know that I'm following Theo Janssen. I've been a fan of his Strand beasts for some 20 years. And in many ways, I consider the crochet coral reef that I'm going to talk about today to be in the same class of activity as a kind of enterprise at the intersection of art, science, and nature. So my talk today is about the poetic enchantments of science. And I want to begin by looking at science as it was conceived in the 17th century when it first came into being. As new types of knowledge come into being, as science did several hundred years ago, they call forth new kinds of institutions. And that was indeed the case when science came into being. A new kind of organization had to, as it were, be called forth from the intellectual mud to deal with this new kind of knowledge making. One of the first of these new institutions was called the Académie de Lincei, that was founded in 1603 by the Italian aristocrat Federico Cesi. Its most famous representative was Galileo, which is why we still remember it with such fondness today. Now, the Académie de Lincei, in Italian, that is the Academy of the Lynx. And the reason it was called the Academy of the Lynx was that the founders believed that the lynx was the lynx was a motto of the new vision they had of knowledge production. The lynx itself was a creature whose observational powers were legendary. And the founders of the Academy believed that, like the lynx, new kinds of observational powers were needed to deal with a new kind of knowledge that they imagined we were moving into. One of the things that they particularly chose about the lynx that they liked very much was that the lynx was reputed to see through rock, and indeed to see through walls. And I love this as an analogy for what science can do. Science today literally does see through rock and see through new walls. The Lincei's motto was lovely. It was, take care of small things if you want to achieve the greatest results. And what they actually meant by that was basically pay attention to the little things, to the mundane things, to the things that perhaps you wouldn't have noticed before. Because by paying attention to these little things, some of the greatest advancements in our understanding come forth. And a fabulous example of this was Galileo's activities. Galileo, much of his work was doing small things. He dropped weights off towers. He rolled balls down inclined planes. He studied the swing of a pendulum. And yet, what came out of this was a grand new physics, an entire new way of seeing the universe. What I want to suggest to you today, and to show you through some of the work that I do, is how we start with little things, small seeds, and how from those grand new ways of seeing and acting come into being. The 21st century is also a time when we are witnessing the births of new kinds of knowledge systems. And commensurate with that, new institutional frameworks in which knowledge can be practiced. We're seeing new syntheses between disciplines and entire new disciplines which have never been thought of before. We have hybrid scientific disciplines such as systems biology, bioengineering, and data-driven genetics. These are brand new enterprises that bring together areas of knowledge such as mathematics with biology, computing techniques with molecular techniques. We're also seeing new kinds of collaborations between the sciences and the humanities, such as medical humanities, which I believe you practice here, and bioethics. We're also seeing new kinds of knowledge partnerships between the sciences and the arts. And I believe here at the University of Iowa, you are leading this challenge to synthesize ways in which we can bring these two great enterprises together. So again, we are seeing, as in the early 17th century, not only new kinds of knowledge, but new kinds of organizations specifically designed to bring forth this knowledge and to deal with the repercussions of it. The enterprise that I'm the head of, that I founded a few years ago, is itself a new kind of knowledge producing system, a new kind of organisation. I founded the organisation with my twin sister in 2003, and its name is the Institute for Figuring. Now, those of you who've got a slightly computer bent in your life might recognise the acronym for our organisation. It's the IFF, which is the logical symbol for if and only if. And what the IFF's mission is our formal motto is that we're dedicated to the poetic and aesthetic dimensions of science and mathematics. One way to think of this is that Christine and I like to say that the Institute for Figuring is a play tank. So you know how we have these institutes in our society now called think tanks, and people come and they think ideas and they write books and they write opinion pieces and they inject ideas into the public culture. Well, we think that's marvellous, but Chrissy and I also believe that we need enterprises and places where people can play with ideas. So that's what we propose the IFF to be, a play tank where people can materially play with ideas and literally see how things play out. This is one of our exhibitions that we had a few years ago, and you'll see just from the very visuals of it that there's a kind of playfulness and a formality involved here. It's almost as if what we're trying to do is to have a scientific front, but underneath show that there is a playfulness to even the most abstract and apparently logical enterprises. Another way to think about this enterprise is in terms of what's now called the STEM to STEAM movement. So STEM, for those of you who may not know, stands for science, technology, engineering, and mathematics. And there has been a move in the last 10 years or so to add art into the mix. So we have science, technology, engineering, art, and mathematics. This is the STEM to STEAM movement. And in a way, the IFF can be thought as part of the STEM to STEAM initiative, but we approach it from a rather different way than many other such enterprises in this domain. And that is that instead of saying, how can we, as it were, bring art into dialogue, into resonance with mathematics and science and engineering, our mission is to say, how can we bring forth into public consciousness the aesthetic and poetic and beautiful dimensions that are inherent within math and science and engineering themselves. So our claim, as it were, is that the STEM activities are themselves aesthetically and poetically enchanted. There's a lovely quote from a Welsh writer, Mary Harper, that I think gets to the heart of what we're trying to do. In a beautiful article, Mary Harper asked, what is the purpose of art? What is the function of the artist? And she says, the duty of artists everywhere is to enchant the conceptual landscape. I realise I've got a typo there. It's the duty of artists to enchant the conceptual landscape. Now, I don't know if it's the duty of scientists and mathematicians to enchant the conceptual landscape, but that is indeed one of the things that scientists and mathematicians and engineers do often achieve. People who study science and math will often tell you that the reason they went into the subject is because they find it beautiful. They find it inherently poetic. And what I hope to show you today is that whatever the duty of science and artists might be, that people involved in these activities are also engaged in aesthetic projects, and we can use their methodologies to bring forth what we might usually think of as artistic objects, artistic exhibitions and exhibits, etc. One of the things that I think it's important to notice about science is the power of science and its beauty is not just in the answers it provides, but also in its methodologies. And one of the things that's important to us at the Institute for Figuring is to say, how can we use the methods of science to produce objects that are fabulous? So our mission is not just to, as it were, present knowledge to the world or to our audience, but to give our audiences an experience of doing things, using the kinds of practices that one might normally encounter in a scientific lab or in a scientific classroom. Practically speaking, what we do at the IFF is multitudinous. This is our website for those of you who might want to have a look up. We do exhibitions, workshops, and lectures with scientists and mathematicians. We publish books. But increasingly what we're known for is participatory programming that engages communities across the world in practices that stand both simultaneously in the art world and in the science world. So I'm going to talk mainly about one project today, which is David mentioned in his introduction, Charles mentioned in his introduction. But that's our Crochet Coral Reef project. But I'll just give you a little hint about another project that we do, which is also a very fabulous project that we're going to be reinvigorating very soon. And that's that we've been working with an engineer, Dr. Janine Moseley, to fold cubes out of business cards. And one might think, you can see the little cubes there, one might ask the question, what can one do with folding cubes? Well, it turns out that what one can do is make an entire landscape of extraordinary objects. The cubes, as it were, become like atomic module, a kind of business card or a business card Lego. And what you can do is produce sculptural objects that have this kind of fantastic modernist power. And this whole field, it's actually formally called business card origami. And the woman who invented it, Dr. Janine Moseley, is a computer engineer. And it turns out there is actually today an entire field of mathematically based origami, which is being explored by engineers, mathematicians, physicists. And Dr. Moseley has invented a sub-branch of this mathematical origami, which is making things out of business cards. A business card is a very formally defined unit that has a particular size. And because of that, as it were, because of the boring regularity of the business card, as it were, all business cards are the same dimensions, at least in America. And you can therefore get thousands and thousands of them and make these little cubes. And you can build bigger and bigger objects. And one thing you can do is build giant mathematical fractals. So here is a fractal built, it's a model, a three-dimensional model of a fractal, which is a mathematical structure. It's made out of 50,000 business cards. It took about 5,000 hours of human labor to produce this object. And it was done through a process, as I say, that was very algorithmic, folding cubes and linking cubes together. And it turns out that there is a whole landscape of these kinds of objects. And it's really extraordinary how something as simple and mundane, as apparently unartistic as a business card, can actually, in the right hands, with creative and logical thinking together, come together to produce such extraordinary objects. The other project that I want to talk about today is a project that we've been doing for 10 years now. I'm really pleased to say the Crochet Coral Reef started 10 years ago. And what we are doing here also is crocheting a coral reef, or crocheting many coral reefs as it's now turned out, based on a principle of mathematics, which is constructing hyperbolic geometric surfaces. So this big orange guy that you see here is an almost perfect mathematical model of what's called a hyperbolic surface. And hyperbolic surfaces are, as it were, an alternative to the Euclidean surfaces that we all study in geometry at school. So at school we study what's called Euclidean geometry, and we learn about the behaviours of parallel lines, and we learn that a triangle has 180 degrees, etc. But it turns out that there are other kinds of geometries, and one of them is this hyperbolic geometry. And believe it or not, it's really quite difficult to make hyperbolic surfaces, but you can do it with crochet. And so this project stands at the intersection of science and mathematics, handicraft, art, environmentalism, and community art practice. So you can see here some of the, that's one of our early installations of a little hyperbolic crochet coral reef. And to give you some sense of scale, that's about 8 foot long, and the coral mounds are about that high. So over the last 10 years, Christine and I have been working with people all over the world to make these crochet coral landscapes. And you see here is an individual model. And you can see immediately the frilly and crenellated forms, which are so reminiscent of corals and so also reminiscent of many other coral reef organisms, such as kelps and sponges and nudibranchs. The project is now, I believe, perhaps the biggest participatory science and art project in the world. Over the past 10 years, we've done it in 35 different cities and countries around the world. There have been more than 8,000 people have now been taught these techniques and contributed individual crochet models to these evolving, ever expanding coralline landscapes. We have exhibitions in art museums and science galleries, such as the Hayward Gallery in London, the Science Gallery in Dublin. This was an exhibition at Art Center College of Design in Los Angeles, which has the great distinction of being America's foremost industrial design college, and is the place where many of the world's car designers are trained. So in a lab next door to where this was displayed, there were people making prototypes of the next generation cars. In recent years, we've decided to go up in scale and to produce much, much bigger pieces. So to give you some sense of a scale, that piece there at the front is about 10 feet tall. This was from an exhibition we did at the Smithsonian a couple of years ago. And here was one of our most recent exhibitions that was held about a year ago in New York University, Abu Dhabi. And what is interesting about these pieces, apart from the scale of them, is that they're all made of plastic. So one of the things that we're doing in the project is responding to the environmental travesty that is happening to wipe out coral reefs all over the world. And corals are faced by many problems, but one of the things they and other marine life are faced with is a huge tsunami of plastic that's going into our oceans. So part of our project is to respond to that by crocheting in plastic. And the one on the left is all crocheted from cut up plastic shopping bags, the white one, and the one on the right is crocheted from videotape, which is another form of plastic rubbish that's gradually filling landfills. So you see here, again, the sense of the scale of some of this. As I said a moment ago, the project is conceived specifically as an artistic response to global warming and the devastation of coral reefs. My sister and I grew up in the state of Queensland, which is where the Great Barrier Reef is. And as many of you know, coral reefs all over the world are being devastated by global warming. In fact, this year, right now, when we have the great El Nino going on in the Pacific, it's one of the greatest coral bleaching events that has ever been recorded. And when we started this project 10 years ago, Chrissy and I joked to ourselves that if the Great Barrier Reef ever died out, our crochet reef might be something to remember it by. In 2005, that was a joke, but in 2015, there's very real talk among scientists that if we don't change our patterns of behaviour, the coral reefs may well die out. The stresses on them due to global warming and ocean acidification are so great that these fragile organisms may not be able to survive the 21st century. So the reason that we decided to crochet a coral reef, if we wanted to make an artistic simulation of these beautiful organisms to draw attention to the environmental crisis facing them, we could have used other artistic mediums. You know, one could have painted a picture, one could have chiseled something in marble. But the reason that we are crocheting them is because it turns out that is actually almost the logically necessary medium to use. These frilly crenellated forms that you see here in crochet are indeed exact analogues of the structures that real corals make. So real corals and nudibranchs and sea sponges have these structures that are their biological manifestations of hyperbolic geometry. And so all these frilly things that you see in nature are actually doing, as it were, they're biologically performing a kind of non-Euclidean geometry. And there's actually a very good reason why so many of these structures appear in the sea. And does anyone want to have a guess about why that might be so? Yes, this man is right. So the reason nature has a love affair with hyperbolic surfaces, and particularly in the sea, is to maximize surface area. If you're a filter feeding animal, like a coral, and you can't go chasing after your lunch and you have to wait for your lunch to waft by you, what you want is maximum surface area to gather as much of it as possible. And that is why hyperbolic surfaces are a great solution. They're also a great solution if you want to propel yourself. So nudibranchs, which sort of do this fluting thing with their frills, that also gives the maximum surface area, which is great for propulsion. So nature has this love affair with hyperbolic geometry. And the irony of this is that although nature has been making hyperbolic things since at least the Silurian age, which is hundreds of millions of years, for humans it's actually not that easy to make such surfaces. And it turns out you can do it with crochet. Actually, for a long time, mathematicians didn't think you could make models of hyperbolic geometry at all. But in 1997, Dr. Dana Taimina, a mathematician at Cornell, figured out that you could do this with crochet. And she said, you know, guys, here we go. We can do it with feminine handicraft. And this was pretty surprising to a lot of mathematicians. And it wasn't that this injected new mathematics into the world, but what it did was injected a model of what had hitherto been a purely abstract thing. So think of it like this. Imagine we all live in a world where you've never seen a curve. Everything is straight lines. And then one day your mathematicians come along and they say, you know what, we've discovered this new thing. It's called a sphere, and it's curved. And all the lines come together at the poles, and it, you know, kind of goes in this swoopy shape. And you go, gosh, I can't imagine that. But you can prove mathematically that this sphere thing exists. And then one day somebody comes along with a beach ball and said, look, I just invented a beach ball. It's a model of this sphere. And you go, oh, wow, now I can see what it looks like. And that's what Dr. Taimina did. She invented a model of a thing that had hitherto only been understood through equations. And just being able to physically hold a model of it in your hand and see it enables people to really grasp it in a way that equations, you can do it with equations, but there's such power in having a physical, tangible model. And so to hold something in your hand has, as it were, not only aesthetic power, but knowledge. It has true knowledge. And that's one of the things that we're interested in with these kind of practices, is that there is knowledge, there is wisdom, there is epistemological power in embodied material objects. And Dr. Taymina and her husband David Henderson at Cornell use these models for teaching for teaching non-Euclidean geometry to their math majors at Cornell. Okay, so let's just have a very brief math lesson about what exactly is the big deal about these hyperbolic surfaces. As I said earlier, hyperbolic surfaces, or hyperbolic space, mathematicians like to use the word space, is an alternative to the Euclidean space that we learn about at school. And actually, you all know a great deal more mathematics than you probably think you do. You're actually already familiar with two different kinds of geometries, which is Euclidean geometry and spherical geometry. So you learn Euclidean geometry at school and think about what you know about the surface of the Earth. So you actually know quite a lot of spherical geometry. And it turns out that hyperbolic geometry is an alternative to these two. There are lots of different ways, or there are a number of different ways of characterizing these three different kinds of geometric surfaces or geometric spaces. But one way is to understand them in terms of curvature. Now, you're all going to feel a bit bamboozled for a moment, and that's okay, because that's what you should be feeling. Mathematicians were bamboozled by this for a very long time, and so should you be. So one way to think about these three structures is in terms of the curvature. A flat or Euclidean space, think about a tabletop, piece of paper, has zero curvature. It makes sense, doesn't it? There's no bumps anywhere, it's just flat. It's zero curvature. A sphere has curvature, and mathematicians have defined it as positive curvature. Now, if you can have something that's a positive curvature space and a zero curvature space, then it kind of makes sense intuitively, doesn't it, that you could have something that's a negative curvature space. So just like there's zero and the positive numbers, and then someone invents the negative numbers, so too, this is the geometric equivalent. So in a way, you can think of hyperbolic space. It's the geometric equivalent of the negative number. Very beautiful. But what does it mean? It is very bamboozling. Mathematicians were nearly driven mad by this problem. Nobody should think that this is intuitive. So let us look at how mathematicians came to this, how they understand this idea of a negative curvature space. One way of describing it is we can think about the properties of what we call parallel lines. And you're all going to show yourselves how much mathematics you do actually intuitively know. So here's a simple question that you all know the answer to. If I have a line and a point outside the line, how many lines can I draw through the point that never meet the original line? 1. So that's what we learn in school, and that's what we know to be true on Euclidean space. On a flat plane, that is true of all lines. But mathematicians have been bothered by this question for 2,500 years, ever since Euclid put forward the idea that there could never be an answer to this that was more than one. Mathematicians have been bothered. Something tugged at the back of their consciousness. And let me show you why there might be an issue. So imagine this is a beach ball. Imagine that circle is a beach ball. So now we have a spherical space, and we can ask the question again. What if I draw a line on my beach ball and I draw a point outside the line? How many straight lines can I draw through the point that never meet the original line? Now we're faced with a very big question. What does it mean to talk about a straight line on a curved surface? That's a very, very complicated question. It took mathematicians a long time to work out a coherent answer to that. And it turns out that on the surface of a sphere, the straight lines can be considered are the lines that are the biggest possible circles, what's called the great circles, like the equator or the lines of longitude. And what's important about those lines and makes them special is that it's always the shortest point. If I trace along one of these great circles, what's called a geodesic, I'm always tracing the shortest possible path between 2 points. Now, every single one of you experiences this in your lives actually in a practical way. What do you think is a situation where actually tracing the geodesics on the surface of, or near the surface of the Earth, becomes an actual practical and money-saving problem? Airplanes. So if you look on airplane routes on the map, they appear to be curved, but they're actually tracing straight lines around the Earth, because by tracing a straight line, you save millions of dollars in jet fuel. So understanding this kind of geometry has very practical real-world applications. So now I've given you lots of hints, and I'm going to ask you the question again. On the surface of a sphere, how many straight lines can I draw through the point that never meet the other straight line? Somebody said the answer? 0 is the answer. Because just as all of the lines of longitude intersect with the equator, so all great circles on the surface of a sphere meet. So now we have a question where there are 2 possible answers. One answer is 1 and one answer is 0. To a mathematician, that immediately says, well, there's another, what about there being another possible answer? Mathematicians are suspicious like that. If there's could be, they're likely to be either one answer or potentially there are lots of answers. And it turns out that there is indeed another answer. And the answer is there exists a mathematically coherent space in which there is an infinite number of lines going through the point that never meet the original line. And those lines are straight. Now, I'm going to prove this to you. So basically, this is a model of hyperbolic geometry, of hyperbolic space, in which it turns out there's an infinite number of these what look like curved lines that go through the point and never meet the original line. And you're all sitting there looking at this and saying you're cheating because the lines look curved. But the only reason they look curved is because we're trying to project a model of curved space onto a flat surface. Just like when I do a map of the Earth, something gets distorted. And so too when I try to project a model of hyperbolic space onto a flat space, things get distorted. But I can demonstrate to you with a crochet model that these lines are straight. So here in crochet is a representation of that. And I can prove to you that these lines are straight because I can fold along them. So that is a physical proof that the most famous proposition in mathematics is wrong. Euclid, for all his genius, got it wrong. There is a space where I can have more than one line going through the point and never meeting the original line. And who would have thought that it could be demonstrated by a feminine handicraft? So just as you can stitch Euclid's theorem, or the proof that Euclid's theorem is wrong, onto these surfaces, you can stitch lots of other mathematical proofs onto these surfaces. You can prove, for instance, that the angles of a triangle add up to less than 180 degrees. And one of the things that's so wonderful about the discovery of hyperbolic geometry is that once mathematicians realized that there were different mathematical possibilities for what the structure, as it were, of a surface could be, it raised the question philosophically, what is the structure of, as it were, the space of our universe? If there are different mathematical options, is it the case that nature has options? And one of the most important questions that we're trying to determine with instruments like the Hubble Space Telescope now is what is the geometric structure of our universe? most of the evidence is that on a very large scale that the universe is Euclidean, but there is some tantalizing evidence that we might just live in a hyperbolic world. So I'm very much hoping that that turns out to be the case. But here we are considering the question of the structure of the universe. And the universe, by the way, whatever structure it is, it's a four-dimensional version of the surface. So think about that. Just, you don't have to comprehend it. But this, imagine that we're talking about something like this, only in 4 dimensions, not 2. Now, it turns out that other things, apart from corals, are also doing hyperbolic geometry, like cactuses. And my favourite example of all is these calla lilies. And it turns out that there's a group of physicists, these are also hyperbolic surfaces. It turns out there's a group of physicists at the University of Austin, Texas, who've been trying to understand how flowers like calla lilies can make these hyperbolic surfaces. And they find that when they do these models, the only way they can make sense of it in their computerized models is to actually model it in 4 dimensions. So isn't that interesting? Human beings struggled with the idea of higher dimensional space for hundreds of years. They spent hundreds of years trying to prove that anything like hyperbolic geometry was impossible. But here we have a flower just effortlessly doing it. And I think it's really interesting to ask the question, does in some sense the flower know 4-dimensional space? I'd like to make a claim that in some sense the flower does. That the flower, by embodying a 4-dimensional paradigm, that in some sense the flower, as it were, knows it. It knows it in the fibre of its being. Equally, I'd like to make the claim that in some sense, when we crochet coral reefers crochet these forms, that what we are doing is a form of experimental mathematics. That the doing of it, the making of these forms, is indeed a form of knowledge production. And it turns out that if you want to make a mathematically perfect hyperbolic surface, like this one by Dr. Taimina, you use a very simple algorithm. Crochet n stitches, increase 1. You just crochet like 10 stitches, increase 1, crochet 10 stitches, increase 1. As long as you do it at as long as you do it at a regular rate, you get a mathematically perfect one. You can do it every 3 stitches, every 4 stitches. But when you make them mathematically perfectly, they tend to look very regular. They look like mathematical models. So really what happened with the crochet coral reef is that we had the realization, or Christine, my sister, had the realization, what if we don't make mathematically perfect ones? What if we do like what this person has done and go out on a tendril, go out on a little limb for a while and then hyperbolicize at the end? What if I make something that is like 2-sided, like this one? What if I do it in beads? What if I go up for a while and then out for a while? And the Crochet Coral Reef project is really coming about because we deviated from mathematical perfection. We stopped following the exact perfect code that produces a mathematically perfect one, the kind of one you'd want to show your students in a class at Cornell. We went wonky and deviant and aberrant. And that's exactly what nature does, because nothing in nature is mathematically perfect. And once you start deviating from mathematical perfection, the forms immediately began to look inherently organic. And nature is like that. Nature is inherently deviant and wonky. It's underlined by codes. Nature has at its heart a DNA code. And just as all life on Earth begins with very simple seeds, the simple seed of a single cell with very simple DNA, well, actually DNA is quite complex in a cell, but you have simple organisms like cells with a DNA code. And as the code complexifies over time, you get the gradual emergence of a tree of life, and one day you wake up and you find you've got peacocks and giraffes. So too with the crochet coral reef. Over the 10 years that we've been doing the project, both Christine and I and our collaborators have gradually morphed the crochet coral code. And all of these codes could, each one of these creatures that you're seeing, you could write the formula down, you could write a pattern and write all the stitches down, just as you can analyse an organism and write down its DNA. But just as peacocks and giraffes do what they do without, as it were, being formally written out by human geneticists, so too we crochet coral reefers, as it were, make and produce with our hands, morphing the code organically as we materially make. And what we've come to realise now is that just as there is a never-ending tree of life on Earth, so too there is a never-ending crochet tree of life. And who would have thought from the simple thing of a feminine handicraft that you would find links between traditional feminine doilies, corals, and the cosmos? And I think one of the lessons of this that I really have come to learn so deeply from this project, and it was an unexpected lesson, is that we live in a world where we tend to silo things. We say the physicists studying the structure of the universe are over there, the marine biologists studying the corals are here, the women crocheting their doilies are over here. And it turns out here that through this project, all these things are interlinked. They are, to use lovely metaphors from fibre arts, they're interwoven. There is a yarn, there is a narrative thread that links disciplines that are normally thought of as very far apart. And for me, this has been the extraordinary, as it were, discovery of this project, that it seems as if once one starts looking and teasing out the threads, that one indeed can find links between the smallest things like sea slugs and crocheting and the biggest structures of all, the structure of the universe. For those of you who might want to know more, I did give a TED talk on this subject in 2009, and you can see that if you'd like. And we have also, there has been a book published on the project that is available for any of you who might like to know more. The book documents not only the art and the science of the project, but one aspect of it that I'll just end on, and that is that the coral landscapes that I've been presenting to you get realized because hundreds and sometimes thousands of people come together to produce them. This is a kind of art that no individual could produce. It is collective in the sense that thousands of people make an ever-evolving artwork. And in that sense, it is a parallel of coral reefs themselves. Coral reefs are made by billions of tiny little coral organisms called polyps, each of which has almost no power on its own, but when billions of them get together, they can build something as magnificent as the Great Barrier Reef, the first living structure that can be seen from outer space. The crochet coral reef, I think, is a metaphor for how we humans can act. Individually, each of us is like a coral polyp. We are insignificant individually, and we cannot change global warming on our own. But I believe that the metaphor of this project is that collectively we can. Collectively, like corals, we can do magnificent things when we work together. And I think that the message of the project ultimately is we are all corals now. So thank you very much. So I know some of you might have to go. It's just before 6:30, but we can stay and have a discussion and questions. So please, I gather Leslie's got a microphone. So if anyone has questions, comments, please put your hand up. And oh, well, actually, let's just give the people who need to go off somewhere else, let's give you time to go. Oh, could you actually, because they're recording, Leslie, could we just wait for the microphone? Oh, okay. We'll come to you next.
So if you go ahead and do your coral reef and you make just a single point error and you watch how it propagates, I mean, does it have a big effect, or is it sort of masked? Like, do you need a number of errors to see a big effect? Like if you were building a regular structure and then had a single mutation or whatever, what happens to the coral?
That's actually a really interesting question. But so here's the question for you. When you say a single point mutation, do you mean like...
Double it up at one.
Sorry?
You add an extra stitch more than you should from your regularity, like you said.
Well, if you simply... Actually, to be frank about it, they're very... If you look at this one, it's regular. It's made... This one's crocheting, increasing 1 every 10 stitches. If I made a single point error, just one error, you probably wouldn't see it. But if I repeat the error, then you will see it. So if I simply make one, if I literally do one mutation, as it were, you probably, a perfectionist would see it, but you wouldn't in general. You have to, as it were, let the error compound, or you have to let the mutation compound.
Have you ever tried to decipher the mathematical formula for an actual living coral organism?
You know, I've quite a number of times had this discussion with marine biologists or coral biologists, and the answer is very little work's been done on this. So I was actually giving a talk at a coral reef conference once, and this coral biologist actually suggested that we write a paper together, which I'd love to do at some point. But no, not a lot of work has been done on that. I mean, these structures are hyperbolic, there's no question of that, but people aren't really going around measuring them. But it raises interesting questions, for instance, like, let me just get to a model. Okay, well, this is a crochet model, but what you can imagine if that was a real coral, like what, for instance, determines why the curves are a particular size? Like, we know this answer in crochet. So Chrissy and I have become very expert at being able to say, I want to make a surface where the frills are on a really fine scale or the frills are on a big scale. So I know I need to use yarn of this size and crochet hook of this size, and I know I need to increase the rate of, you know, X, Y, or Z. So we've actually become very, as it were, expert on this question in the domain of crochet. But when I've asked coral reef biologists, like, what determines whether a real coral curls this much or that much, they don't know. So there are actually a great deal of things that just simply aren't known at the moment.
You said, I think, that your sister was the one who figured out the crochet process of manifesting this, and I'm just curious if you could talk a little bit more about what that discovery, how that happened, or what it was like.
Yes. Well, the real innovation that Chrissy made was when she said, when she said, look, I don't want to stick to the mathematical formula. So to make this one, as I said, you use a very simple algorithm. Crochet n stitches, increase 1. And n can be 3 or 4 or 29 or whatever. As long as I increase at a regular rate. So that just means I crochet, say, 6 stitches, increase 1, crochet 6 stitches, increase 1. As long as I do that at a regular rate, I will get a mathematically correct hyperbolic model, the kind of thing that you would want to show in a math class at Cornell. But they don't have much difference. If I make, it can be a little one, it can be a big one, but it doesn't really have much variation. It's a bit like, think about a sphere. You can have a little sphere, a medium sphere, a big sphere, but all spheres look the same. After a while, all the real hyperbolics look the same. So Chrissy's innovation was to say, I'm not going to stick to the mathematical formula. I'm going to start going wonky. So what say I increase once every 3 stitches for a while, then I increase once every 4 stitches for a while, then what say I just go out here because I feel like it. And I have to say that there was a bottle or two of champagne involved in this occasion, and we were watching episodes of Xena Warrior Princess. So the moment of realization came about under the influence of alcohol and warrior women. And I think these things are related. And I have to make a personal confession here, is that Chrissy and I are twins. When we left school, she went to art school and I went to university and studied physics and mathematics. And I was the one who kept saying, oh, we have to stick to the mathematical formula. And one day Chrissy just came home with a bag of pink, fluffy, sparkly yarns that she'd bought at the local Michael's store and a bottle of champagne and said, I'm branching out. I'm not going to stick to the mathematical principles anymore. I'm going to deviate. And it was amazing. Within literally a single night, we had a group of them on our coffee table and we looked at them and we said, oh my gosh, they look like a coral reef. And Chrissy said, we could crochet a coral reef. She likes to remind me it was in the conditional tense. We could crochet a coral reef. And 10 years later, we have. But the thing that was amazing to me, because I come from this science background, was, oh my gosh, what happens when you break the rules? And as Chrissy likes to remind me, if it had been up to me, we would have never progressed out of the Silurian age. And that's what I've learned from this project, is because I come from a science background and she comes from an art background, is, oh my gosh, get over it, break the rules, please do. And that was really the innovation, is don't stick to the formula, just see what happens. And things have happened that we would never have imagined. For instance, this one, that's knitted in wire. It's knitted in a kind of wire that it attaches chips to circuit boards. This one, I mean, who would have ever guessed that you could make these tall, some of those tall spires are actually perfect hyperbolics. And there are actually real species of corals that look like that. So nature has learned to play. And one of the lovely things about this is that the more we do this, the more that we realise that in some very profound sense, nature and livingness is all about breaking the rules, of finding the poetry in the code by doing what writers do and just saying, I'm just simply going to play with it. I'm going to play with the words. I'm going to play with the letters. and see what transpires from that. So we do actually think of this as a kind of material poetics. And I do think that's something that one can understand living creatures in that way. You know, in some sense, a peacock or a giraffe is a kind of living poetics. There is a code underlying it, it's DNA code, but it's not till it's realised in material form that you see the true magnificence of the being in itself. And the being is not just reducible to the code, it's matters as well. Oh, if you could.
You said several times that that crochet is a traditionally feminine handicraft. Were many of your volunteer coral reef crocheters men?
That's a really great question because the answer is yes. There have been a few, but of the 8,000 people who contributed models to the various reefs around the world, 99.99% of them have been women. And that's really surprised us. I mean, we always imagined that if the project took off, that there would be more women. But if I'd guessed at the beginning, I probably would have said maybe, you know, 1/3 men, 2/3 women. But it's been almost all women. I mean, really, there have been a few dozen men. And it's really kind of surprised us why that is the case, because crafts become very groovy. There are guys doing craft. There was a big exhibition a few years ago called Radical Knitting and Subversive Lace, and at least I think over half of the people in the exhibition were guys. So why haven't guys come to the Reef Project in greater numbers? It is a mystery. Sorry?
I'm curious, what part of Australia did you live in, and did you have much knowledge of the barrier reef corals before you made this inebriated discovery?
We grew up in Brisbane, which is the capital of the state of Queensland. So the Great Barrier Reef is in the state. It runs along the coast of Queensland, but Queensland's a very big state. So it actually starts about 1,000 kilometres north of Brisbane. So I hadn't ever seen the Barrier Reef growing up, but the Great Barrier Reef looms large in the consciousness of Australians. So I think Australians are very, very aware that we are the custodians of the reef and that it's on our watch that it's getting sick. And so like all Australians, I think we all feel a great attachment. And when I went to it, finally, it is the most beautiful, beautiful thing. It's really extraordinary. You feel like you're on another planet. And it's so worthy of our protection and care.
So you had created it in yarn before you actually got the chance to do it firsthand in Newlands?
No, I had actually seen the Barrier Reef before we began the Reef Project, but I hadn't seen it growing up. The Barrier Reef's quite a long way away from a lot of things. It's one of those things that I think all Australians hold in their heart, whether they've been there or not.
Hi. I want to ask you a question over here. What is that fourth dimension?
Thank you. Well, you know, this question sometimes comes up, and I'm intending to write a whole book on the subject. What do we mean when we say that something is 3 dimensions or 4 dimensions or 2 dimensions? It's a very, very deep question. How much time have you got? So I'll attempt to give you a little bit of it. So we say that this is mathematicians would say that this is a two-dimensional surface, and you can think of that as being that there's, as it were, an x and a y coordinates that I can literally define any point on this surface by saying go this much up here and go this much along there. Just as I could do, on the flat plane, I can say, the Cartesian grid, I can say go 3 units along and 4 units up. If I want to define a point in this room here, I need 3 dimensions. I need to say to you, go this, go 3 units in this direction, 4 units in that direction, and 5 units in this direction. So we have an x, y, and a z axis. So we say that this space that we're in is a 3-dimensional space. Now, you can't visualize, or most people can't visualize, a higher dimension. But you can think theoretically, as I've just shown you, that we can just simply add a dimension, we can just add another coordinate. I can say x, y, z describes any point in this room. Just use your imagination for a moment and say, what if I just say, I'm going to say, I need 4 points to define, or 4 numbers to define a point. So I'm going to say x, y, z, and p. And then if I want to have 5 dimensions, I just say x, y, z, p, and q. Now, you know how I can write on a, if I wanted to find points on a piece of paper, I can say, put the x, comma, y in brackets. And if I want to have 3-dimensional space, I go x, comma, y, comma, z in brackets. Do you all understand that? That I can write down that code? Okay, so up until about the late 19th century, mathematicians thought that's all you could do too. You could just go x, y, or x, y, z, because that's the way the physical world is, they thought. But here's the thing, and this is why mathematics is true poetics. What happens if I just say, that's just a code? And why does the code have to be restricted to 2 or 3? I can just go x, y, z, a, b, c. I can write out a string of numbers followed by 1 number, 2 number, 3 number, 4 number in brackets, and say that's just a code for a 99-dimensional space. And one of the great realizations of mathematics in the 19th century was that mathematicians realized, whatever word you want to use, in the late 19th century, that the codes that they wrote down didn't have to be related to anything physical. So, as it was famously said by the great mathematician De Morgan, he made the claim that mathematics doesn't have to be about anything other than itself. And so if you have that notion that mathematics isn't about anything other than itself, then I can write down any code I like. So I can say, here's a code for a 4-dimensional space. Here's a code for a 3,700-dimensional space. And then you say, well, what does that relate to the world? And the answer for a mathematician is, who cares? That's your problem. My physicists have the problem of relating the codes to the physical world. And we believe that on the large-scale structure, the universe has 4 dimensions. That's because that's the way general relativity says it. But as far as mathematics goes, a dimension is just simply that code. And it doesn't have to be anything other than that at all. So for a mathematician, a dimension is just a word that we use for one parameter of the code. But a physicist has the problem of, does the dimension have a physical instantiation? But here's a really beautiful thing that is, we talk about space as having 4 dimensions. Okay, this room has 3 dimensions, but general relativity talks about space as having 4 dimensions because it includes time as a particular dimension of space. But here's the thing, why do we privilege the things that we call space and time as the dimensionality? So, backwards, forwards, up, down, left, right. I can write that down as X, Y, Z. And then in relativity, I can add another one and say time. So it's backwards, forwards, left, right, up, down, time, bracket, 4-dimensional space. Well, who made that decision? That's totally arbitrary. What if I want to say backwards, forwards, up, down, right, left, time, temperature,
Right?
weight, colour, smell? Who gets to decide? And here's a beautiful thing. In the 17th century, Descartes said, what about the proposition of everything that we could measure, every conceivable quality in the world, is another dimension of reality? So when we say how many dimensions does the world have, well, it depends what you want to class as a dimension. And actually, this whole era of big data, what's at the heart of that is what big data scientists do is that they just measure everything and they say, okay, I'm going to, let's say we're talking about your health, I'm going to measure your age, your weight, your height, your blood pressure, your blah, 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 and that's the information that defines you, and I might have 300 dimensions on you. So as far as they're concerned, the big data people, you're a 300-dimensional data set. And so actually what's happening now in the era of big data is Descartes' vision of saying everything's a dimension of reality. And we don't just privilege space and time. It's just that in order to show what they do, the models that the simulations that they make on with their computer models have to be done with a data set that has another. So that's why it's a difficult question to answer, because the 4th dimension in this case doesn't have a physical analogue. It's like saying, in order for my model to work out, I have to add this other thing in, but it doesn't have a physical analogue. And this is something that happens all the time in physics, that people realize that in order to model the phenomenon, I'm trying to think of a way to it's almost as if the mathematics has a mind of its own, and the math won't work in 3 dimensions, but it will work in 4 dimensions. And that's actually something that happens a lot. Once you get into mathematical modelling of things, I mean, you can physically measure the world and then say, how can I make the models from just those parameters? But you can also, sometimes the math just asserts itself and said, I'm not going to work in 3 dimensions, I'm going to work in 4 dimensions. So I'll just tell you a very simple example of this, which may just bamboozle you further. But there have been attempts to have, there are kinds of numbers that are 2-dimensional. They're called you will have probably all heard of them, but there's a kind of number called the imaginary numbers. And that actually has a very technical mathematical meaning. And the imaginary numbers go together with what's called the real numbers. And it's a two-dimensional number set. And they turn out to be realized in all kinds of real-world systems. For instance, if you want to understand electricity going through your house, you have to use these two-dimensional numbers with the reals and the imaginaries. There have been attempts to say, can I have a three-dimensional number set? But it turns out it doesn't work. You can have two-dimensional ones, you can have four-dimensional ones, you can have eight-dimensional ones. So that's 2 by 2 by 2 by 2. You can't, but 3 or 5 doesn't work. So somehow the math has a mind of its own in cases, and that turns out to be the case with the flowers. So I think we might have, one last question?
Yes, I've got one more question for you, and it's back to the land of crochet versus thinking hard. When you agreed to fill a giant space with a coral reef, and your sister said, I have to crochet like mad, thanks for that, little miss. What was her favorite something to use, and did she just make up different things along the way? Did she use different variations throughout the 8 months of creating that? And did she have a favorite type of yarn or hook or the like?
Well, the question is that when the first time we had a big reef show, we'd done a really little one at the Andy Warhol Museum, and then we got invited to do it at the Chicago Cultural Center, and they said, we've got a 3,000 square foot gallery and we'd like you to fill it with corals. Now 3,000 square feet is a huge, huge space. That's, I don't know, twice the scale of this room. It's a huge space. And my I, in my ignorance, because I was a science person, said, oh, yes, yes. And I came home and told my sister, and she just said, you're out of your mind. That's just huge. But she went into crochet overdrive and really spent most of the next year, when she wasn't teaching her job at CalArts, crocheting. But one of the things that she did, which was very courageous, is that she took up crocheting plastic and videotape. And actually, plastic's a hard medium to crochet with because you have to cut it all up. It's hard on your hands. But Chrissy really pioneered making crochet with videotape and with plastic. And lots of people who, I'm just going to show you quickly images of that. So these guys. Lots and lots of people admire this part of the project for its ecological, as it were, message, but very few people are prepared to actually crochet with plastic because it's hard on your hands, it's not easy, you have to cut it all up. The videotape, actually, the oxide comes off on your fingers and it's toxic. But it's really, really powerful, and I think Chrissy has single-handedly crocheted more plastic than everybody else put together.
What a fascinating talk and Q&A. Thank you so much.
Thank you, Dave.
Please come back and join us on April 12th to hear Sarah Lewis.
Thank you. Thank you. And I realized, David, I called you David, not Charles. Yeah.
Charles is my father's
Yeah.
name.
Yes.
So I thought, oh, good, that will become a family thing. I think somebody wants to say.
Thank you. Absolutely, yes, yes.
This is
When it-
the most, I just got it
Oh.
from your foundation.
Thank you.
So, and it arrived